Hi guys, and welcome to this new episode of The Inexplicable. I dedicate this episode to everyone with blind faith in science. All the incurable skeptics who only trust what has been proven by the scientific method and who think that the scientific community always has all the answers, or almost all of them. Well, after what you're about to hear, your certainties will start to waver. There was a time when science was convinced that heat was an invisible fluid flowing inside objects, or that life could be created from nothing. And did the public believe it? But what happens when science instead is wrong? Marcio? Today I'll take you on a surprising journey through 7 historical cases where scientific theories, accepted as indisputable truths for decades or even centuries, were spectacularly disproven. Get ready to see how even science can be wrong and how mistakes often spark major revolutions in human knowledge. So here are 7 incredible cases when science was certain but completely wrong. The Ice Age that never came was a period not too long ago, at a time when the scientific community and public opinion seemed to share an almost unanimous belief. That is to say, that in a short time, a new ice age would occur. This is not an urban legend, nor a modern conspiracy theory, or a Hollywood exaggeration. We are talking about a real phenomenon experienced in the 1970s when major and authoritative newspapers, including a famous 1975 article published by Newsweek titled "The Cooling World," spread a disturbing alarm. Our planet was cooling rapidly, and a new ice age could be on the way. The implications were terrible. Falling temperatures could have put global agricultural crops at risk, caused devastating famines, pushed entire nations to the brink of economic collapse, and destabilized the world's geopolitical balance. But what was really behind that alarm? What was the real situation behind appearances? From the late 1940s to the early 1970s, scientists observed a cooling trend, although slight and gradual, especially in the northern hemisphere of the planet. This phenomenon had a very specific and scientifically based cause: industrial pollution caused by the strong economic and productive recovery after World War II. Factories, power plants, and industrial activities, they emitted huge amounts of aerosol particles and fine dust into the atmosphere, which reflected sunlight back into space, temporarily decreasing the amount of heat that reached the Earth's surface. In practice, these particles acted like a sort of natural screen, capable of cooling the air. A real, measurable, and well-documented dynamic, but essentially temporary and local. However, this observation, which did have scientific basis, ended up becoming an impressive media case. This triggered alarm in many parts of society, excessively amplified by the media and by some particularly alarmist scientific circles. Anyway, while some climatologists focused on the possible risk of an ice age, the majority of the scientific community began to observe very different and much more worrying signs. A slow but steady increase in global temperatures, closely linked to the rise in concentrations of carbon dioxide and other greenhouse gases in the atmosphere, caused by human activities. These forecasts, based on emerging climate models, clearly indicated that the planet was warming and not cooling. Despite this fundamental part of the scientific debate was largely ignored and underestimated by the media, because the story of the new ice age was too sensational and captivating for the headline to go unnoticed. The visual shock and fear from a hypothetical global freeze amplified alarm well beyond its scientific significance. The result of this communication error was a misunderstanding that lasted for decades. Even today, among those who are skeptical about climate change, the argument circulates that climate science is uncertain, contradictory, or even unreliable. They cite that famous Ice Age alarm from the 70s as proof of failures and changes of course in scientific theories. But the reality is very different. It was a classic case of media amplification of a minority of studies, often misrepresented or taken out of their original context. A communication error, not an error of science itself. In hindsight, the case of the so-called global cooling represents a fundamental lesson on how science works. We can consider it a dynamic process made up of hypotheses, experimentation, data collection, continuous revisions, and yes, even temporary errors. Theories are refined over time as new evidence and technologies emerge. When only alarming and sensational headlines are chosen while ignoring established scientific consensus, it risks creating a distorted and harmful narrative. Today, thanks to much more sophisticated climate models, decades of satellite data, and planetary observations, we know for sure that the real threat to our future is not an ice age, but global warming caused by human activities. Exactly. And so that theory of an imminent ice age slowly melted away like snow in the sun, leaving behind a valuable lesson. Never stop at first impressions. Never. Cold fusion? Let's take a step back in time to the year 1989. The world is still deeply marked by the tension of the Cold War, an era when the fear of a global nuclear conflict loomed over everyone's heads. Video stores are full of video home system tapes with movies and documentaries that tell of a future halfway between hope and fear. In this climate of uncertainty, two American scientists, Stanley Ponce and Martin Fleischmann, became the protagonists of an event destined to shake the foundations of modern physics and ignite hopes that were nothing short of revolutionary. At a dramatic impromptu press conference, the two chemists and electrochemists announced a discovery that seemed straight from science fiction. According to them, they had managed to achieve nuclear fusion at room temperature on a regular laboratory bench. Did you get it right? The so-called cold fusion? A reliable, replicable process could forever change our civilization, promising unlimited clean energy with no harmful emissions, radioactive waste, or risks linked to traditional nuclear power plants. But how did it work? Well, the experiment consisted of passing an electric current through heavy water, which is enriched with deuterium, using a piece of palladium as an electrode, a metal capable of absorbing large amounts of hydrogen. Ponce and Fleischmann claimed that the heat produced by the experiment far exceeded what one would expect from a simple chemical reaction, suggesting that some form of low-energy nuclear fusion was actually being triggered. The news spread around the world at an astonishing speed. Newspapers ran headlines like, "A new era of energy is at hand," and "The energy of the future is already here." Obviously, scientific laboratories and universities on every continent rushed to try to replicate the experiment, hoping to usher in a future free from dependence on fossil fuels. There was already talk of energy revolutions, space satellites powered by compact batteries, cold fusion, and a world where energy would be accessible and inexhaustible. However, the enthusiasm and wonder lasted only a very short time. A crucial problem soon emerged. No one, outside of Ponce and Fleischmann's laboratory, seemed able to convincingly replicate the results. In fact, many of the replications provided inconsistent data or showed no indication of nuclear fusion at all. When the scientific community began to ask for precise details about the experiment, the two scientists were vague and reluctant. They avoided providing complete data and did not allow thorough independent verification. Transparency, the foundation of the scientific method, was completely absent. Within months, cold fusion was seen as a great illusion, The official scientific community, the rigorous one, made up of numerical data, repeatable experiments, and peer reviews. Trapari dismantled Pons and Fleischmann's work piece by piece. It was discovered that the supposed signs of excess energy were probably due to measurement errors, interference, and simple experimental noise. Cold fusion turned out to be essentially a colossal hoax, a media flash in the pan with no solid foundation. But this story, more than a defeat, became a valuable lesson for the entire scientific community and for anyone approaching extraordinary discoveries. The story of cold fusion teaches us that in science, extraordinary claims require extraordinary evidence, not triumphant announcements or emotional press conferences. Total transparency, methodological rigor, and above all, the ability to subject every result to the tough test of replicability and time are needed. Despite everything, the so-called ghost of cold fusion has never completely disappeared. In the following years, a small but persistent group of researchers continued studying similar phenomena under different names, like low-energy nuclear reactions. Some of them claim that with modern technology, which is much more advanced than that of the late 80s, certain unusual thermal anomalies could finally find concrete explanations. However, to this day, no one has yet been able to provide clear and irrefutable evidence that can reproduce cold fusion or its derivatives at the heart of the scientific scene. The lesson is clear in research as in life. You must always maintain healthy skepticism and a rigorous respect for the facts, letting the truth emerge only after patient and rigorous work. Work that clearly the two scientists didn't even come close to doing. N-rays. At the beginning of the 20th century, world physics was in a moment of extraordinary fragmentation. X-rays, just discovered by Wilhelm Röntgen a few years earlier, had revolutionized the understanding of matter, opening new doors to science and medicine. Meanwhile, radioactivity, studied by pioneers like Marie Curie and Henri Becquerel, was captivating Europe's brightest minds, fostering an atmosphere in which it seemed that every month brought with it a new truth or a scientific revolution. Amid this enthusiastic intellectual fervor, in 1903, a highly reputed French physicist, René Blondelot, made an announcement that would shake things up, scientific community. He had identified a new unknown form of radiation, which he called N-rays, in honor of his hometown, Nancy. According to Blondelot, N-rays, they were an invisible, extremely subtle and mysterious radiation, capable of influencing the brightness of objects, making them brighter and shinier, and even able to pass through materials that normally block visible light. Blondelot didn't just come up with a theoretical hypothesis. He claimed to have personally observed and measured these rays with experimental equipment in his laboratory, thus proving their existence in a concrete way. These claims of his deeply impressed the French scientific community, and surprisingly, many other scientists in the country rushed to replicate the experiments, apparently confirming his discoveries. In just a few months, over 100 scientific articles with data, graphs, and testimonies appeared, seemingly confirming the existence of N-rays beyond doubt. The excitement and enthusiasm grew rapidly. In France, Gliese rays were considered a possible revolution comparable to the discovery of X-rays, a new frontier for physics, with potential applications ranging from medicine to telecommunications. But not everyone was convinced. Some foreign scientists remained skeptical, finding the elusive and almost magical nature of the N-rays unconvincing. But Brownlow's prestige and the many publications appeared to confirm the phenomenon's reality. Amid rising doubt and curiosity, Robert Wood, an American physicist known for his critical spirit, rigor, and unconventional investigations, intervened. Robert went to Brownlow's laboratory himself to witness this enigmatic phenomenon. Wood was famous for exposing errors and scientific false alarms, and what he discovered became one of the most famous cases of collective illusion in the history of science. During a public demonstration, Wood performed a gesture as simple as it was ingenious. He secretly removed a crucial prism from Brownlow's experimental apparatus, an essential component without which, if the arrays had really existed, it would not have been possible to detect them. Yet Brownlow, unaware of the sabotage, continued to claim he could see them, and even described in real time the effects they were supposed to have on the objects. This inconsistency clearly showed that his perception was the result of an illusion. Wood published a detailed report on the episode, exposing the myth of the arrays and quickly bringing down the entire house of cards built around this supposed discovery. Within a few months, scientific interest in the arrays plummeted dramatically, and the international community recognized that it was a huge case of self-deception, a clear example of respected scientists falling victim to distorted expectations. Today, the case of the arrays is studied as a classic example of confirmation bias, that psychological mechanism by which we tend to see only what confirms our expectations, ignoring or rationalizing everything that contradicts them. Blondlow and his colleagues had not acted in bad faith or with the intention to deceive, but had simply been misled by their own minds, victims of social pressure and enthusiasm. The moral is very clear. Enthusiasm and the desire to make great discoveries should never replace the core principle of the scientific method. Verification must be independent, experiments repeatable, and rational skepticism essential. Only through these tools is it possible to distinguish truth from falsehood and protect science from errors, illusions, or even worse, outright deception. Aware. The substance that wasn't there. For centuries, science presented a thesis it viewed as absolutely certain. That is to say that every wave needed a medium to propagate. Sound, for example, travels through air. Sea waves are in water. And light? Well, for 19th century physicists, even light had to travel through something, and so the concept of the luminiferous ether was born, an invisible, intangible substance, impossible to detect, but considered absolutely real. It was meant to fill the universe. It had to be everywhere, even in the deepest space. It was the missing element, the elegant explanation for how light could travel through the cosmic void. The luminiferous ether was accepted, discussed, and taught, a pillar of classical physics, until two men, armed with an extremely sensitive instrument, decided to really put it to the test. It was 1887, and physicists Albert Michelson and Edward Morley wanted to measure the movements of the Earth through ether. To do this, they built an interferometer, an extraordinarily precise machine capable of detecting the slightest variations in the speed of light. If the ether existed, the Earth's movement should have altered the speed of light in one direction compared to another, like wind that changes a sailboat's speed. But the result was absolutely nothing. No variation, no ether wind, no evidence of its existence. It was a real shock, a paradox. Light seemed to always travel at the same speed, regardless of the Earth's motion. Scientists didn't know how to explain it. The academic world was baffled. How can light move without a medium? And then, in 1905, a young clerk from the Bern Patent Office appeared on the scene. His name was Albert Einstein, and with his theory of special relativity, he swept away centuries of mistaken beliefs. According to his equations, light didn't need any medium. It travels through a vacuum, and its speed is a constant of the universe. In one fell swoop, the luminiferous ether was wiped out, a substance that had never existed, a ghost born from the human mind, yet it had lasted for centuries. Sometimes the entire scientific community can firmly believe in something that simply isn't true, and it takes a failed experiment or a revolutionary mind to open their eyes, in this case that of our dear Einstein, the phlogiston. I imagine living in the 17th century. Fire is everywhere, in fireplaces, in torches, in furnaces, but no one really knows why things burn. And so the brightest European scientists ask themselves the question, what is fire? What is that mysterious force that consumes wood, coal, animal fat? The answer came with disarming speed: phlogiston. According to this theory, every flammable substance contained an invisible principle, an entity called phlogiston, which was released during combustion. Fire, then, was nothing more than the release of this element. When a piece of wood burned, the phlogiston would go into the air, and what remained, the ash, was simply the true matter, stripped of that burning principle. For over a century, this idea attracted chemists, philosophers, and scholars because it worked and matched everyday observation. Everything that burned left residues, metals once calcined with heat, changed appearance, so there had to be something that went away, right? But no, wrong, completely wrong. What challenged the theory was a small but significant detail: the mass. When metals were burned, the result, the so-called calxes or oxides, weighed more than the original metal. But how was that possible? If the phlogiston was lost, then the mass should have decreased, not increased. At that moment, Antoine Lavoisier, a man who would forever change the history of chemistry, entered the scene. With meticulous experiments and a scale in hand, Lavoisier showed that nothing was lost during combustion. The oxygen in the air combined with the matter, generating new, heavier compounds. It was a real revolution. Forget about phlogiston. Fire was the result of a precise chemical reaction, observable and measurable. With the publication of his results in the last decades of the 18th century, Lavoisier not only killed the phlogiston theory, he also laid the foundations of modern chemistry and the principle of conservation of mass. But what this story teaches us is even deeper. Even a beautiful, coherent, and widely accepted theory can be completely wrong, and progress often comes from the courage to question what seems obvious. Because in science, as in life, it's not enough to seem true, it has to actually be true. The steady state theory. I imagine I'm a scientist in the mid-20th century. The night sky is a boundless enigma, and one question dominates the brightest minds of the time. Did the universe have a beginning, or has it always existed? On one side, there's the Big Bang theory, which speaks of a violent primordial explosion, an absolute starting point that gave rise to everything we know. But this fascinating idea comes with a major problem. It suggests a beginning of time, which many scientists then found almost philosophically unacceptable. And this is where a thesis comes into play, as elegant as it was ultimately wrong: the steady state theory, supported by brilliant minds like Fred Hoyle, Hermann Bondi, and Thomas Gold. According to them, the universe had neither a beginning nor an end. It was expanding. Yes, but to keep its density constant, new matter was spontaneously created in the void, as if the cosmos itself was eternally self-regenerating. A fascinating, almost poetic vision. No initial explosions, no point of origin to explain, just an eternal universe, unchanging in its overall structure. For a while, this theory held up. The observations of the expansion of the universe weren't enough to favor one hypothesis over the other. Big Bang and steady state seemed to be on equal footing, but then something happened that changed everything. In 1965, two scientists from Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate an annoying background noise from a radio antenna. No matter what they tried, that persistent static wouldn't go away. It didn't come from the Earth or the Sun. It was everywhere. That disturbance turned out to be the cosmic microwave background radiation, a faint thermal glow that permeates the entire universe. An echo from the primordial event, just as the Big Bang theory predicted. It was the lingering heat from a young, dense, scorching universe, still visible billions of years later. For the steady-state theory, that discovery was a condemnation. Not only had it not predicted the existence of such radiation, but it couldn't even explain it. It was as if the cosmos had whispered its true origin into the scientists' ears and said, "Yes, I actually had a beginning." And within a few years, the scientific community abandoned the steady-state theory en masse. This was relegated to the fringes of cosmology, surviving only in modified or speculative forms. The steady state was a refined theory, supported by great minds. But the reality of the universe, as often happens, had a much more surprising truth in store. Life from nothing. And to conclude this overview of scientific theories that had to be consigned to the oblivion of scientific thought, I can't help but mention the craziest one, that of spontaneous generation. For almost 2,000 years, humanity took for granted something that today seems at least absurd to us. Life can arise from nothing. Yes, you heard that right. According to a very ancient belief called spontaneous generation, insects, worms, and even small animals could emerge directly from inanimate matter, like rotting meat, mud, or piles of grain. The philosopher Aristotle was among the first to formulate this idea, which seemed intuitively certain to everyone. How could one not notice that small worms appeared on rotting meat or frogs in muddy puddles? And again, who wouldn't think mice might come from piles of rags and grain? Even in the following centuries, this belief persisted, finding prominent supporters during the Renaissance. For example, Van Helmont claimed that by leaving a dirty cloth in grain for 21 days, it would spontaneously give rise to a colony of scholars. But all of this began to waver in the 17th century, when an Italian doctor named Francesco Redi decided to put this theory to the test. He performed a simple but revolutionary experiment. He put meat in different jars, some sealed tightly, others covered with a thin gauze, and others completely exposed to the air. Only in the meat exposed to flies did larvae appear, while in the sealed and covered jars, absolutely nothing developed. Redi showed that worms came from fly eggs, not the meat itself. A first important refutation of spontaneous generation. Still, despite the evidence, the idea persisted in later centuries. In the 19th century, French scientist Louis Pasteur conducted one of the most famous experiments in science history. He used a glass flask with a swan-shaped neck containing a sterilized nutrient broth. Air could enter, but impurities and microbes remained trapped in the curved neck. The broth remained sterile until it came into contact with microbes from the air. Pasteur showed that life comes only from existing life, not from nothing. This result marked a real revolution. Spontaneous generation had been definitively disproved. From there, the germ theory, modern cell biology, and consequently medicine as we know it today were born. This story teaches us a fundamental lesson. Even when science seems confident, it can make spectacular mistakes. Even deeply held beliefs backed by daily observation can be overturned by rigorous experiments. The story of spontaneous generation is an early example of how the scientific method changed our understanding of life, teaching us to question especially what seems obvious to us. And so we come to the end of this journey through bizarre errors of science. That moment when human knowledge, so self-assured, turned out to be profoundly wrong. Science, with all its precision, its experiments, its formulas, is ultimately a human creation, and like every human creation, it is inevitably fallible. The certainties we now take for granted and the theories we view as unquestionable foundations of knowledge, one day, maybe 100 years from now, they could be seen as the most glaring mistakes of our time. Think about it carefully. And what if some of the scientific theories that seem so solid to us now, in a century, seemed ridiculous or even worse, actually harmful? It's a question that opens our minds, that invites us to never stay too attached to what we think we know. Science is not a dogma, but a constantly evolving journey, an open story that is written day by day, even thanks to mistakes. It's from these mistakes and setbacks that new discoveries and revolutions emerge. And now the floor is yours. Which of these scientific theories that turned out to be wrong impressed you the most, and why? But above all, which theory or certainty of modern science do you think could one day turn out to be wrong? Let me know in a comment. The Unexplainable is an original format, written and directed by Luca Perella, sound design by Matteo D'Alessandro. If you enjoyed this episode, leave a like, subscribe to the channel on YouTube, or share it with your friends. See you next time on The Unexplainable.